Hello guys, it's Caller from 19. Today is day 53 in my challenge day. And the last week we I've just looked around and some reviewed the Monte Carlo concept again. And just finally now I'm going to learn about the resampling, important sampling to make uh, the performance of the sampling and at the same time to get unbiased resulting image. Okay, that's my goal to learn. Okay, then let's start. So one of the main problem of Monte Carlo integration was variance, because it serves a problem of probability. By the nature of the probability, it has some variance, which is called error in the resulting image. And um, we felt a need for the robust reduction technique to make a better image. And the resample importance sampling is like one of the technique to reduce variance with the robustness. This robustness. So
Hi, I'm DJ, and in this video, I'm going to explain importance sampling. My reason is simple. I have a long list of machine learning topics I'd like to cover in the future, and importance sampling shows up a few times as a trick. And that's all it takes to make it as a video topic. Now, it turns out it's difficult to understand importance sampling in a vacuum. It'll make a lot more sense if we motivate it from the perspective of Monte Carlo methods. So let's dive right in. These techniques are concerned with one extremely important task that shows up a ton in machine learning: calculating expectations. Without going into too much detail, expectations are very frequently the answers that many of our ML algorithms are seeking. They show up when fitting models, doing probability queries, summarizing model performance, training a reinforcement learning agent, just a load of stuff. Now, mathematically, that means we like to calculate this. Here, x is a continuous random vector, boldface means it's a vector, and p of x is the probability density of x. F of x is just some scalar function of x we happen to be interested in. Now, you should think of this as the probability weighted average of f of x over the entire space where x lives. To communicate that, it's often written like this. As an aside, if x were discrete, then this integral would turn into a sum. Considering none of the concepts really change for the discrete case, we'll continue with the continuous case. Okay, now the problem is, sometimes, in fact, a lot of the time, this integral is impossible to calculate exactly. Typically, it's because the dimension of x is high, so the space it lives within is exponentially huge. And so we have no hope of adding everything up within it. And this is where Monte Carlo methods come in. The idea is to merely approximate the expectation with an average. This average. What this says is we collect n samples of x from the distribution P, plug those into F, and take their average. It turns out that as n gets large, this thing approaches our answer. For the sake of brevity, let's call this S. To get a feel for this, let's play with a one-dimensional example. Let's say p of x is this, and f of x is this. In this case, things are simple enough such that we can calculate the answer exactly. To do that, we look at the product function and calculate the area under the curve. This is the truth we're after, but please use your imagination and pretend we can't actually calculate the area this way, because in the general case, it can be impossible. So instead, let's approximate this area using Monte Carlo. First, we sample x's from P and then plug those into F. The average of these is an approximation to the integral. To emphasize, the core of Monte Carlo is to say this average is an approximation to this area. I'm not proving that, but trust me, it's true and very important. Frankly, it's more important than importance sampling. Okay, one thing to point out is that this average S is random. If I were to resample everything, I'd get a new S, and I could keep doing this. This means that our sample average has its own distribution. In fact, let's check that out. Let's say the true expectation we'd like to estimate is this value. Also, let's say we repeat our estimate many times, giving us many S's. Now, we're in a better position to view the distribution of S. Now, to avoid confusion, this distribution is just useful for theoretical understanding. In applications, we only get one sample of S. Keep that in mind as I talk about this thing. Okay, the first thing to notice here is the distribution is centered on the true expectation we're after. This is a critical property. When we have it, we say our estimate is unbiased. Also, looking at this, we can see that the variance of S, something which tells you about the width of this distribution, matters a lot. It gives us a sense of how off a single estimate is likely to be from the truth. Now it turns out the variance of S is the variance of f of x scaled down by n. Okay, one other thing. Notice this distribution is a normal distribution. Where did that come from? Well, that's the central limit theorem. It's a magical and super famous result. And in this case, it says it does. It's a magical and well, that's the central limit other thing. Notice this distribution is a normal distribution. Where did that come from? Well, that's the central limit theorem. It's a magical and super famous result. And in this case, it says it doesn't matter what P or F are. No matter what, as n gets large, this will get closer and closer to a normal distribution. In fact, we can summarize this by writing this. To repeat myself a bit, this says S's distribution approaches the normal as n gets large. The mean of that normal is the expectation we're trying to calculate. And its variance is the variance of f of x scaled down by n. Please take a second and absorb all that. Done? Excellent. You're now ready to learn about importance sampling. We start by introducing a new distribution, q of x. As we'll see, this is something we get to choose. And again, we are interested in the same expectation we had earlier. Note, this still involves p of x. Okay, now, here's the trick of the century. We're going to take this term and multiply it by q of x over q of x, which is just 1. We can do this without damaging anything as long as q of x is greater than 0 whenever p of x times f of x is non-zero. And that gives us this integral. Looking at how I've bracketed things, we can see that it's the probability weighted average of a new function, where the probability is given by q instead of p. So, just like we did earlier, we can write that like this. Stepping back, this says the p probability weighted average of f of x is equal to the q probability weighted average of f of x times the ratio of p to q densities. That's the trick. Now, if we look at this and we recall the lesson of Monte Carlo, we can estimate this with samples from Q. What I mean by that is this expectation, which is equal to the original expectation we're interested in, is approximately equal to this average, where the xi's are sampled from Q. Let's call this new average R and ask, what's the advantage of using this? Well, first, it's unbiased, just like in the previous case. And second, it has a new, possibly improved variance. That is, the variance of R, which gives us a sense of how off from the truth a single sample of R is likely to be, is the variance of F times the density ratio, where samples are generated according to Q, scaled down by n. So the hope is we can choose Q such that this variance is less than the variance we dealt with earlier. Now, to do that, it turns out Q should say x's are likely wherever the absolute value of p of x times f of x is high. That's a key result, which I'm not proving, but it kind of makes sense when you recognize that we are trying to estimate the area under the p times f curve. Got it? Okay, it's about time we do an example. To help, here is a little summary of the core ideas we're demonstrating. Okay, let's do an example where importance sampling will reduce the variance quite a bit. In particular, let's say p of x is this, and f of x is this. As a point of reference, let's estimate without important sampling. Notice how much our estimate is bouncing around. This is because f is large only in rare events under p. So a small set of samples have an outsized impact on the average. Now, important sampling can help us here because we can make it sample the more important regions more frequently. In particular, I'll make q of x this. But now, if we'd like to use q samples, we need to adjust the f function. So let's do that by multiplying it by the density ratio, which gives us this. The ratio, which gives us, so let's do that by multiplying it by the density ratio, which gives us this. To declutter things a bit, I'll drop p of x. Okay, now after this adjustment, we can proceed just like we did with plain Monte Carlo. That is, we sample from Q, pass those into the density ratio adjusted F, and then calculate their average. This is our new estimate. And the whole point is, if we repeat this process, we'll get something that bounces around less than if we sampled the previous way. That's the whole idea. The variance is reduced, and with a single estimate, we expect to be less wrong. Okay, so there you have it. And if you're like me when you first learned this, you're a bit
In the previous videos, I mentioned importance sampling, and I showed that importance sampling only lets us calculate quantities of interest, like a normalizing constant, the mean, etc. But unlike rejection sampling, we don't actually end up with a sample from the distribution we wanted. So in this video, I will show you how this can be achieved using sampling importance resampling, or SIR. And first I'll explain the technique. I'll show you how to obtain a sample from f of x and prove why the technique is correct, or at least try to give you some intuition into it. And then I will also show you how it's easy to move from f of x, a current distribution, to a sample from another distribution quite easily using the SIR algorithm. And finally, I will show an example in R. Okay, so what is sampling importance resampling? Remember that in importance sampling, we use the trick that in order to calculate f of x, this is equal to f of x divided by g of x times g of x, where g of x is a proposed distribution, something that is a distribution which is easy for us to calculate. And in importance sampling, we sample from this easy distribution and then calculate this thing over here. So what the SIR algorithm says is take these things and consider them as weights. So take these things and what the SIR algorithm says is take so distribution and then calculate this thing over here. So
Understanding data structures and algorithms is difficult. Don't worry, log2base2 can help.
Hi, here's the trick. Of P to Q.
In the previous videos, I mentioned importance sampling to achieve intuition into a sampling importance resampling. Where g of x is a proposed distribution, this thing over here, from this easy distribution, and then calculate this thing over here. So what the SIR algorithm says is take these things and consider them as weights. So weights of I is fx of I divided by gfx of I when xi was drawn or sampled from the distribution G. Now, once you calculated these weights, the SIR algorithm tells you to normalize them. So we can consider Q of I to be W of I divided by the sum of all W of I. Now take the sample that you drew and resample from it according to these probabilities. So we are resampling from the sample that we already obtained. So let's say we obtain a vector, yeah, of x1, x2, all the way to some xn, yeah? And for each, we have a chance to take x1 according to w1 divided by the sum of all w's. And some xi, we have the chance to draw it wi divided by the sum of wi. And what SIR tells us is that the new sample that we get, those new, let's call them x tilde i's, the new sample that we get will be from the distribution of the normalized f of x. So this is quite cool. We only sample from some easy distribution, but after going through all the process, after calculating the weights, normalizing them, and then resampling from the sample that we had before, before distribution, but after going through all the process from the tells us is that the new sample take x1 according to w1 the reach all the way to some xn, yeah, and for
So the last week, although I just studied the sampling importance resampling method, but at the moment I just didn't understand the fully didn't understand the what is the exact concept of this SIR. But I just do keep recap for just with the several YouTube video. So basically, again, the importance sampling is we take a easy distribution to take a sample from the distribution. And we also want to keep the focus, we want to focus on the more important region in the distribution. So for example, if the px looks like this and the f of x looks like this, the variance part of fx, f of x is more concentrated in the right side, but because the px, PDF of x, P, probability density of x is concentrated on the left side, we always pick the samples from the left side more frequently. But for the fast convergence, we need to move on the sampling on the right side so that we can just more get the unbiased image as fast as possible. So for this, we do some tricks that we multiply a new distribution, new easy distribution, q of x over q of x, which is the ratio is equal to 1. So it's just a mathematical trick. So we multiply the both term of the equation. So we get a uh, new target function that is move on the region of that we are interested in, the more probabilistically happen the reason. So whenever we take a samples from with the new distribution, now we just can concentrate on more important reason from now on. And the basic idea of the SIR is to use this converted function uh, um, as a weight function, except for just the multiplier q. So, for example, if we uh, take take account for weight I, weight I is equal to f of xi over q of xi. The samples from the sample xi is drawn by the distribution of q, and for our I, we normalize the specific weight of I by their summation. Then we get a new probability G of I. And then we sample new samples from the samples already taken by Q. So we have samples like x1, x2, x3, and so on. And we take new sample from these samples by under the new distribution GI, right? Okay. This is the basic idea of the SIR.
Each, we have a chance to take x1 according to w1 divided by the sum of all w's. And some xi, we have the chance to draw it wi divided by the sum of wi. And what SIR tells us is that the new sample that we get, those new, let's call them x tilde i's, the new sample that we get will be from the distribution of the normalized f of x. So this is quite cool. We only sample from some easy distribution, but after going through all the process, after calculating the weights, normalizing them, and then resampling from the sample that we had before, we end up with a sample of the desired distribution. And this sample will be from the normalized desired distribution. So why is it so? Well, let's first consider the CDF of f. So this is the CDF of f, and remember, f of x is still not, doesn't have to be normalized, yeah? So this will be the integral of f of x dx from, let's say the support of x is the entire real line. So this will be until a, and since f of x is not normalized, we have to normalize this. Okay, we can use the importance sampling trick. Minus infinity to a, we can write this as an integral from minus infinity to infinity time the indicator function for minus infinity till a. Yeah, and what this means is this function is 1 from minus infinity to a and 0 elsewhere. Now this is, we can look at this also as the expected value, the mean, with respect to some distribution g of f of x divided by g of x times the indicator function. This is the same. Okay, so let's call this thing over here, instead of f of x divided by g of x, wi of x. And the I means we are going to sample from g, so x of I will be sampled from g. And then this can be approximated by the sample average.
applies for the fact that the density of the sample is 1 and only approximation. The density is simply 1 approximation. Sampling density and P the purpose density must be greater than 0. Okay, so I just finished the basic part of the resampled importance sampling. And before I'm going to end up today's recording and just recap first. So why we need resampled importance sampling? So Monte Carlo integrator has a variance. We need a robust variance reduction technique for better image. And the resampled importance sampling, the advantage of resampled importance sampling, the shortly RIS, is a robust variance reduction technique, and it doesn't require any other prior knowledge of the distribution of the target distribution. So the basic way to solve integral I of a function f of x is equal to this. But if we use the Monte Carlo integration estimator, we can apply, we can represent it like this. But the q hat is normalized, should be normalized and easy to sample, while we are using a rejection or inversion sampling method when we sample. This is some of the constraints that we encountered using the standard Monte Carlo integration. So to reduce variance in a robust way, we need to modify it a little bit. So we did a quick review for SIR, and the basic steps of RIS. So what is RIS? What is RIS algorithm? So to generate samples from Q hat, we use SIR. And the samples generated by SIR are only approximately distributed according to Q hat. When we take care of the weight function as Wj is P of J and Q of J. And the P is the proposer density, source distribution, and the Q is the sample distribution that we use when we take a sample from the proposer samples. So we must add a weighting term to the standard Monte Carlo estimator to maintain unbiasedness of it. And for generality, allowing the weighting term to be a function both the proposers and the resulting samples, we can represent the integral with the RIS method like this, with a weighting function. The Q should be unnormalized and the density of the samples yi is only approximate Q hat. But this weighting function is simply the average of sum of weights, like this. So by combining these two equations together, we get a basic RIS estimate. And for RIS to be unbiased, below two conditions should be satisfied. And the one is sampling density Q hat and proposer density P must be greater than 0 everywhere that F is non-zero. And NN must be greater than 0 because it is placed in the denominator term. So it's trivial condition. And from the next sections, the paper mentions about problem from the basic RAS estimator. I think it's time to end up today's recording. Okay. Thanks for watching and bye bye.